urgent. Any urban transportation network operates on a fragile physical limit. When a sudden demand shock hits an area, the physical movement of vehicles degrades and the infrastructure chokes. For global ride-hailing platforms, managing these acute spatio-temporal demand spikes is the core engineering problem. A stadium emptying out creates an instant, massive localized request volume that the physical supply of nearby cars simply cannot meet. In the first seconds of this shock, the system matches every available vehicle in the immediate vicinity to a rider. The local supply pool instantly drops to zero. This graph visualizes a switched nonlinear ODE model, the mathematical framework governing marketplace traffic. It tracks two queues, price-sensitive and price-insensitive riders, plotted against supply capacity. When the demand curve spikes above the matching rate, unsuppressed request volume actively outpaces the physical service rate. This specific state triggers a catastrophic system failure, known in queuing theory as the wild goose chase equilibrium. Mechanically, the dispatch algorithm must still fulfill the incoming requests. With local supply depleted, it searches outward, pulling cars from increasingly distant geographic zones to service the high-demand area. For the fleet, drivers spend their operational time in long-distance, unpaid, en route states, driving toward pickups rather than transporting passengers. Because vehicles are locked in inefficient routing, the platform's effective carrying capacity drops to zero. The marketplace entirely stalls. Surge pricing exists to prevent this exact cascading queue collapse. By applying a price multiplier, the system reduces the volume of the price-sensitive queue, keeping demand strictly below the physical matching threshold. Executing this emergency control mechanism in real time requires a highly specialized architectural blueprint. The engine relies on three critical layers operating in sequence. First, spatial discretization, next, stream processing, and finally, algorithmic smoothing. Calculating localized supply and demand ratios on demand creates an immense database latency challenge. Traditional relational databases that rely on standard counting queries fail completely at this scale. If millions of concurrent requests attempt distance-based joins over dynamic driver locations, row-level database locks and severe read latencies will crash the platform. To survive high-throughput environments, systems architects must decouple heavy state ingestion from the lightweight pricing calculation API. The system cannot calculate state on the fly, it must constantly maintain it. The first architectural layer requires discretizing the physical world into a structured mathematical grid. You cannot measure local supply without defining what local means. This map illustrates a traditional approach, overlaying a city with a square geographic grid, like a geohash or Google S2 system. A square grid introduces a severe mathematical flaw for dynamic movement models, non-uniform adjacency. A cell has two distinct types of neighbors. Cardinal neighbors sharing an edge sit at a distance of 1, but diagonal neighbors sharing only a vertex sit further away, at a distance of the square root of 2. This geometric distortion skews any algorithm attempting to calculate local driver supply density and physical travel times. The distance calculation contains an inherent directional bias. To fix this, Uber developed the H3 hexagonal hierarchical spatial index. This diagram shows a square grid morphing into an H3 hexagonal grid. The core geometric advantage here is uniformity. All 6 neighbors share an identical edge length, and all 6 are equidistant from the centroid. This uniform radial distance eliminates directional bias entirely. It allows algorithms to track driver movement and execute perfect spatial smoothing across the grid. H3 also utilizes an aperture 7 multi-resolution hierarchy, allowing the grid to recursively scale up to larger areas where data is sparse, or down to tighter boundaries where data is dense. Surge pricing algorithms operate precisely at H3 resolution 7. An area of roughly 5 square kilometers provides the exact balance between hyperlocal geographic accuracy and a statistically stable pool of drivers. The second layer focuses on aggregating raw telemetry data into that H3 spatial grid in real time. The system must track an immense volume of chaotic, overlapping inputs, millions of asynchronous driver GPS pings and rider app queries firing simultaneously, every second. All of this raw telemetry is immediately ingested into a distributed event streaming platform, typically Apache Kafka. This flowchart tracks the data pipeline. Telemetry from the apps routes into the Kafka message bus, which then feeds directly into a stream processing engine like Apache Flink. Flink consumes these massive streams and maintains stateful rolling time windows, like 1-minute and 5-minute intervals, independently for every single H3 cell on Earth. By tracking active driver locations against incoming ride requests per cell, Flink continuously computes the exact live supply-to-demand ratio. These computed counts need a final destination, a low-latency feature store, usually built on Redis. The final data model is elegantly simple. Flink stores the complex computed ratio as a basic key-value pair tied directly to the H3 cell ID. When a rider opens their app, the Fair Estimation API queries the Redis store directly. It completely bypasses the heavy stream computation happening in the background. Unlike the naive database approach that locks and stutters under load, querying a pre-computed ratio in Redis achieves sub-millisecond read latency. Stream processing serves as the vital translation layer. It transforms erratic, asynchronous physical movement into a perfectly synchronized, globally queryable system state. The final architectural layer converts those queried supply and demand counts into an actionable pricing decision. The formal mathematical trigger for this decision is the supply gap index, which the system recalculates every 8.3 seconds. This equation on screen represents the index. The first variable is the inverse of the active driver count within a 0.4-mile radius. As cars disappear, this value climbs. The second variable tracks the median time to accept for pending requests in that zone over the prior 90 seconds. The third variable factors in the historical cancellation rate for that specific spatial zone and time of day. When this aggregated index crosses a critical threshold, typically 1.8 on a 5-point scale, the system immediately activates a surge multiplier. However, applying prices purely cell by cell creates severe price cliffs in the physical world. A rider could see their fare double simply by crossing the street into an adjacent hexagon. This visual maps a central H3 cell and the mathematical solution to those cliffs, K-ring spatial smoothing. The engine aggregates driver supply across neighboring concentric rings using a weighted sum distribution. Ring 0, the origin, carries a 1.0 weight. Ring 1 carries a 0.4 weight, and Ring 2 carries a 0.1 weight. By decaying the influence of distant drivers, K-ring smoothing mathematically guarantees seamless gradient price transitions across a city's geography. It ensures fairness and prevents arbitrary price spikes at grid boundaries. We can now observe what happens to the system state immediately after that surge multiplier is served to the rider app. The ODQ experiences an immediate feedback loop. Price-sensitive riders delay their trips, dropping out of the queue and instantly capping the runaway demand curve. Simultaneously, the supply reacts. The elevated multiplier attracts nearby available drivers, incentivizing them to reposition directly into the high-demand H3 cell. This chart graphs the surge multiplier's exponential decay. The slope is governed by physical constraints, an 8.3-second driver reaction time and a 14.2-second rerouting latency. At 180 seconds, it predictably drops to 83%. At 420 seconds, it falls to 77%. This decay curve yields an evidence-based rider strategy. By deliberately delaying a ride request by 3 to 7 minutes, a user allows the system to stabilize. Empirical data shows this brief temporal delay eliminates the surge entirely in 68% of urban scenarios. Surge pricing is a vital synthesis of hexagonal geometry, stream processing, and queue management. It is the precise engineering required to preserve the physical integrity of a global mobility network under pressure.